Hi, I'm Dr. Robin, aka Double O Pi. This video is the third of what will probably be a 5-video series on metal-ligand complexes. In this video, I'm going to talk a bit about how and why these complexes form. If you haven't watched the previous 2 videos, please do so before watching this one. The links are down in the description below. Today we're going to be talking about how to calculate equilibrium concentrations of individual metal-ligand complexes. In my last video, I talked about how we can use 2 different types of equilibrium constants for metal-ligand complex formation. The stepwise constants are indicated by the traditional case of F, while the overall constants are referred to as beta. This video exclusively uses beta values to calculate equilibrium concentrations. If you want to learn about how to use the stepwise constants, that will be in the next video. Let's talk through the steps to follow when solving for the equilibrium concentrations of metal-ligand complexes. You first have to know how many complexes might form, and for that you're going to consult a table of formation constants. Once you know which constants will form, you'll write an equilibrium constant expression for each of the complexes. When you're first starting, you may need to write the formation reactions first in order to do that. Next, you're going to rearrange that equilibrium constant expression so that you have the concentration of the complex on one side of the equation and everything else on the other. Then you'll write a mass balance equation for the metal and replace each of the terms of that mass balance equation with the expressions you found in step 3. At that point, you'll be able to solve for the concentration of the free ion. And once you have that, you can solve for the concentrations of all the complexes. Now, of course, these steps never make much sense until you actually use them on a problem, so let's go ahead and do that now. Here's our first problem. We have a system that was made with 0.0040 molar cadmium-2+ and 0.38 molar oxalate. If you were actually going to make the system, there would be some other ions present, so technically there might be all sorts of chemistry going on in the system. However, we're not going to deal with that right now. We're just going to pretend that the only sort of equilibrium chemistry happening in the system is metal-ligand complex formation. So what we're going to do with this system is first solve for the concentration of free cadmium that would be present at equilibrium, and second, solve for the concentration of the cadmium-oxalate ions that are present. The first step is to figure out how many cadmium-oxalate complexes would form, and for that we turn to our table of complex formation constants. We first find the table for oxalate anions, then we look for the row with cadmium. We can see that there is only one beta value, which means that we will only form one cadmium oxalate complex. Also, note that the value in that row is a value for the log of beta 1, which means that we're forming a complex with one cadmium and one ligand. Okay, now we're on to step 2, which is to write an equilibrium constant expression for each complex. In this case, we only have one complex, so we'll only need to write one equilibrium constant expression. Since you're just learning how to do this, I'm going to start by writing the reaction for the complex formation. Again, this is going to be a complex made up of one cadmium-2+ ion and one oxalate anion. Now that I've written that reaction, I can easily write our equilibrium constant expression beta as a function of concentrations. The next step is to solve the expression for the concentration of the metal-ligand complex. At the beginning, this concentration should be in the numerator of your fraction. So solving for the concentration involves multiplying both sides by what's in the denominator. Here we see that the concentration of the cadmium oxalate complex is equal to the beta value times the concentration of cadmium-2+ times the concentration of oxalate. Step 4 is to write the mass balance equation for the metal. The total amount of the cadmium in the system must be equal to the sum of all the cadmium containing species in the system. So our total cadmium concentration must be equal to the concentration of free cadmium, that's cadmium that's not bonded to anything else, plus the concentration of the cadmium oxalate complex. Now, our original problem actually said how much cadmium was put into the system, so we can add a number to this mass balance equation. The total amount of cadmium must be 0.004 molar. In step 5, we replace as many terms in our mass balance equation as we can with expressions we derived in step 3. You may remember that we came up with this expression for the concentration of our cadmium oxalate complex earlier, and now we're going to substitute it in here like this. Step 6 asks you to solve for the concentration of the free metal ion, which is the concentration of cadmium 2+. Here's the mass balance equation that we derived in the previous step. The first thing we're going to do is find an actual number to use in place of beta 1. To do that, we look at our table of beta values for oxalate and locate the row for cadmium 2+. This says that the log of beta 1 is 3.71. So our beta 1 value will be 10 to the 3.71. Next, we're going to make an approximation. We have far more of our ligand in the system than we have of the metal. There's almost 100 times more oxalate than there is cadmium. So we're going to assume that the concentration of free oxalate will remain more or less constant at around 0.38 molar. Let's substitute that number in for the oxalate concentration. All right, where do we go from here? Well, you can see that each of the terms on the left side of the equation contains the concentration of free cadmium. So we're going to factor that out like this. Notice that there were 2 terms in that earlier equation, and now we have the free cadmium concentration times an expression in curly brackets that has 2 terms. The first term in the curly brackets 1 comes from the free cadmium concentration in the earlier equation, while the second term comes from the concentration of the cadmium-oxalate complex. Now that we have this, we are almost ready to answer part A of the original question, how much cadmium 2+ remains in the free metal form? The way to get the final answer is to divide both sides of the equation by what's in the curly brackets, like this. And when you put that into your calculator, you find that the concentration of free cadmium is equal to 2.1 times 10 to the minus 6th. The last step involves solving for the concentration of the cadmium-oxalate complex. In step 3 of the process, we found the expression that will help us do that, and at this point we should have all the numbers we need. We have our beta value from the table of complex formation constants, we have our concentration of free cadmium, which we found in the previous step, and we have our concentration of oxalate, which was given as part of the original problem. Plug those numbers into a calculator and you'll get this answer. But if you round to the correct number of sig figs, you'll see that basically all of our cadmium has ended up in the complexed form. Let's look at another cadmium complexation problem, this time using bromide as a ligand. Once again, we're going to calculate both the concentration of free cadmium and the concentrations of all the cadmium-bromide complexes. Again, the first step is to identify the number of complexes that will form. Here we can see that there are 2 beta values for cadmium-bromide complexes, beta 1 and beta 2. So we will form 2 cadmium-bromide complexes, one with 1 bromide ligand and one with 2 bromide ligands. Now that we know what complexes will form, we can write the formation reaction for each complex and use those reactions to write the equilibrium constant expressions. We can then take those equilibrium constant expressions and rearrange them to solve for the concentrations of each individual complex. Now we get to write a mass balance equation for the metal. Our total cadmium concentration must be equal to the concentration of free cadmium plus the concentration of the cadmium complex with 1 bromide ligand plus the concentration of the cadmium complex with 2 bromides. And based on the information given in the original problem, we know that these concentrations must add up to a total of 0.0024 molar. Now that we have the mass balance equation, we can substitute the expressions we derived in step 3 for the concentrations of each of our cadmium-bromide complexes. Now we're going to take that equation that we just generated and we're going to plug in the numbers we know. Remember that the values given here are not our actual beta values, but rather the log of beta. So those are going to be the exponents in our equation. We can also assume that the concentration of our ligand will not change significantly, so we can take that concentration from the problem and substitute it in here. Okay, now we have an equation that has 1 variable, the concentration of cadmium 2+, as well as a bunch of numbers. And again, we're going to isolate that variable by factoring it out of each term of the equation. We can then solve for the concentration of free cadmium by dividing both sides of the equation by what's in the curly brackets. Now we have an equation that has our unknown concentration on one side and a bunch of numbers on the other. Putting this all into our calculator, we get a free cadmium concentration of 7.87 times 10 to the minus fifth. Now that we have the concentration of the free ion, we can go ahead and calculate the concentrations for each of our cadmium-bromide complexes. We'll start with the expressions that we derived in step 3, and then we can plug in our beta values, our concentration of free cadmium, and our concentration of bromide. And then just a quick pass through the calculator gives us our concentrations. Before we move on to the next problem, I want to compare the answers to the two problems we've done so far. These have both been cadmium problems. You'll notice that we started with different concentrations of total cadmium, so it probably isn't too surprising that we ended up with different amounts of free cadmium. I'm also going to pop the molarities of cadmium complexes up here. One thing you'll notice is that for both of these problems, most of the cadmium ended up complexed instead of remaining in the free metal form. You'll also notice that in problem 2, the cadmium complexes had concentrations that were very close to the same. So you might ask, is that normal or is it just a coincidence? Well, for many metals, it actually is pretty common for the majority of the metal to end up being complexed. But how much gets complexed? Let's throw in some percentages here. For example, in problem 1, only 0.05% of the metal stayed in its free metal form, while in problem 2, it's 3.2%. So even if there's just a small fraction of the metal remaining in that free metal ion form, how small that fraction is will vary based on equilibrium constants. All right, let's move on to our last problem. We're going to be looking at a solution of tin here. Notice that there's no ligand given in this particular problem. I did that on purpose to talk about one of the reasons that complexation is so important to understand. Our tin exists in a fairly basic solution, pH 11.5. What does that mean? It means there will be a lot of hydroxide present. And since hydroxide is a Lewis base, it can serve as a ligand. So what we'll be looking for in this problem is concentrations of tin hydroxide complexes. Let's start by calculating the concentration of hydroxide. At a pH of 11.5, our H plus concentration will be 10 to the minus 11.5. Our hydroxide concentration will therefore be 10 to the minus 14th divided by the H plus concentration, 3.16 times 10 to the minus third. All right, let's go through the steps we've been using. The first thing you want to do is look at a table of complex formation constants to find out how many complexes will form. We have values for beta 1, beta 2, and beta 3, which means that we'll form 3 complexes. One with 1 hydroxide, one with 2 hydroxides, and one with 3 hydroxides. Before I move on, I want to warn you that I'm going to be moving through this problem pretty fast. I advise you to pause the video as needed so you can follow what I'm doing. But because we've done this before, I'm assuming you can figure out most of the math with very little prompting. Okay, in step 2, I'm writing out the formation reactions for each complex to help you see how I come up with the equilibrium constant expressions. But hopefully by now you can start to see the pattern in how these equilibrium constant expressions are formed. When I'm looking at complex formation equilibria in my own work, I don't write out the formation reactions, but I have a decade plus of working with these sorts of equilibria, so I'm very comfortable with the patterns. With enough practice, you'll get there too. In step 3, we rearrange those equilibrium constant expressions so that the concentration of the complex is on one side and everything else is on the other. Again, the best way to do this is to multiply both sides by the denominator of the fraction. Now we're going to write our mass balance equation for tin. This time we have 4 terms: the concentration of free tin, the concentration of the complex with tin and 1 hydroxide, the complex with tin and 2 hydroxides, and the complex with tin and 3 hydroxides. And of course, we can use the information in our problem to set this equal to an actual number. Now we're going to take our mass balance equation and plug in the expressions we came up with in step 3. For step 6, we get to take all of the numbers from the problem, from our hydroxide calculation, and our table of complex formation constants, and plug them all into the mass balance equation. Don't forget that the complex formation constants are listed as the log of beta rather than the actual beta values. That's a common mistake I see on people's exams. Notice that the equation we come up with is pretty messy, which is the reason I don't attempt to do systems with 4 or more complexes on YouTube videos. But despite being a really long equation, we solve this exactly the same way we did with the shorter ones. We take our equation and factor out the concentration of free tin from each term, which will give us this equation. Next, we divide both sides by the expression in curly brackets. And as before, this gives us an expression that we can plug into our calculators. Now, if you do that, the number that you get for your concentration of free tin is 2.25 times 10 to the minus 23rd. And now that we have our beta values and both our free tin and hydroxide concentrations, we can calculate the concentrations of each of the complexes. So let's plug those numbers into our expressions and calculate the concentrations. Before we finish the video, let's look at the concentrations of our tin species one more time. We started with a total of 1.8 times 10 to the minus 5th molar tin. How did that get distributed? Well, as you can see, we ended up with a very tiny amount of free tin left. This concentration is considerably smaller than anything we saw in the previous two problems. And there's another difference. In problem 2, we ended up with roughly equal amounts of our 2 cadmium complexes. But this time around, you can see that the concentrations of the 3 complexes are very different. In fact, if we look at the composition as a percentage of the total, you can see that there's an almost negligible amount of our first complex compared to the third or even the second complex. Why is it so different from last time? Because we have different complex formation constants. Before we get into the summary, if you found this video helpful, please take a moment to click all of the things to engage with the YouTube algorithm. So today I walked you through a simplified method for how to calculate equilibrium concentrations of metal-ligand complexes. The way I've taught you to do this assumes that the metal ion is the limiting reagent in solution, which is often true. But what if it's not? Then we have to treat this as a more complex system involving the systematic treatment of equilibrium. But that's a topic for another video. Thanks for watching. I'm looking forward to seeing you again on the channel soon. Dr. Robin, signing out.